Welcome to our deep dive into writing custom Linux system calls. This advanced topic is crucial for anyone looking to build ultra-scalable systems or optimize kernel-level interactions. System calls are the fundamental interface between user space applications and the Linux kernel, allowing programs to request services like file I/O, process management, and memory allocation. Understanding existing system calls is the first step, but being able to extend this interface opens up a world of possibilities for specialized applications. Today, we'll cover the what, why, and how of creating your own system calls, laying the groundwork for more efficient and tailored system designs. So, why would you want to create your own system calls? The primary reasons often revolve around performance, security, and specialized functionality. For instance, you might need highly optimized data paths for network processing that existing calls don't provide, or a secure way to access specific hardware resources without complex user space drivers. Custom system calls can enforce strict security policies, ensuring that only trusted kernel code handles sensitive operations. They also enable kernel-level optimizations, reducing context switching overhead compared to inter-process communication mechanisms. This level of control is invaluable for high-performance computing, embedded systems, and security-hardened environments. Before we dive into coding, let's ensure our environment is ready. You'll need a Linux development machine, preferably a virtual machine, to avoid potential issues on your primary system. Crucially, you'll need the Linux kernel source code matching your target kernel version. For example, if you're running Ubuntu 22.04 with kernel 5.15, download the 5.15 source. You'll also need development tools like GCC, Make, Flex, and Bison, which are standard for kernel compilation. Familiarity with C programming, basic Linux commands, and kernel concepts is essential. Setting up a dedicated VM and ensuring you have the exact kernel source code will save you significant headaches later on. The Linux kernel source tree is vast, but we only need to focus on a few key areas for custom system calls. The Arch directory contains architecture-specific code. You'll typically be looking at arch/x86/entry/syscalls for x80 systems. The include/uapi/asm generic directory holds generic system call numbers, while architecture-specific ones are in arch/arc/include/uapi/asm. The actual system call implementations will reside in a new or existing C file, usually within the kernel directory or a new module directory. Becoming familiar with these paths will greatly streamline your development process. The core of integrating a new system call involves adding an entry to the kernel's system call table. For x86-64 systems, this typically means modifying arch/x86/entry/syscalls64.tbl. Each entry requires a system call number, an ABI, application binary interface, the name of the system call, and the function it maps to. For example, you might add 333 common my custom syscall sys my custom syscall. The system call number must be unique and within the allocated range. This table is the kernel's dispatcher, translating your user space syscall invocation into the correct kernel function call. Carefully select your system call number to avoid conflicts. Once you've added the entry, you need to write the actual C function that the kernel will execute. This function, typically named sys_my_custom_syscall, matching our example, takes arguments directly from user space. It's crucial to understand kernel data structures and memory management when implementing this function. You must never dereference user space pointers directly without proper validation using functions like copy from user or copy to user to prevent security vulnerabilities. Your function will live in a new .c file, for example, kernel_mysyscall.c, and needs to be added to the kernel's build system makefile. This is where the core logic of your custom functionality resides. With the kernel-side implementation complete, we need a way for user space applications to call it. While you can directly use the syscall library function with your system call number, it's generally better practice to create a wrapper function. This wrapper, often defined in a custom header file, provides a more readable and typesafe interface, mimicking how standard library functions work. For example, long my custom syscall int arg1 const char argtil would call syscall 333 arg1 arg2. This abstraction simplifies development for applications using your new system call and promotes code clarity, making it easier to maintain and debug. This is where your changes come to life. The process involves configuring, compiling, and installing your modified kernel. First, configure your kernel, typically by copying your current kernel's configuration /boot/config-uname-r. Then run make menu config to verify settings. Next, compile the kernel using make-j nproc for parallelism, which can take a significant amount of time, often 30 to 60 minutes or more depending on your system. After compilation, install the new kernel modules and the kernel itself. Finally, update your bootloader, e.g. grub, and reboot into your new kernel. Thorough testing is critical at this stage to ensure stability and functionality. Debugging kernel code is inherently more challenging than user space applications. Standard debuggers like GDB aren't directly applicable without special setups. Key techniques include using printf for logging messages to the kernel ring buffer, which you can then view with dmessage. Attaching a kernel debugger like KGDB via serial port or network can provide more powerful debugging capabilities. For tracing system call execution, strace in user space is invaluable, showing your custom system call being invoked. Remember, a bug in kernel space can easily crash your entire system, so incremental testing and careful logging are your best friends. As you venture into custom system calls, remember that kernel code runs with the highest privileges. Therefore, security and stability are paramount. Always validate all user space inputs to prevent buffer overflows, integer overflows, or privilege escalation. Minimize the attack surface by making your system calls as atomic and specific as possible. Document your system calls thoroughly, including their purpose, arguments, and return values. Consider upstreaming your changes if they have general applicability, or maintaining them as a patch set for specific deployments. Never expose sensitive kernel data directly to user space without sanitization. Following these best practices will help ensure your custom system calls are robust, secure, and maintainable.